When people hear the term Big Bang, they often imagine a massive explosion, a single moment when everything suddenly burst into existence from a tiny point into empty space. This image is powerful, dramatic, and deeply misleading. The Big Bang was not an explosion in space. It was not a blast expanding outward from a center, and it did not happen at a specific location within the universe. In fact, the Big Bang is not really a thing that happened at all, at least not in the way we usually think about events. The theory of the Big Bang is a scientific model, a mathematical description of how the universe has been expanding and cooling over time. When scientists look at distant galaxies, they see that space itself is stretching, carrying galaxies away from each other. When they trace this expansion backward, they arrive at a state where the universe was hotter, denser, and more compressed than anything we can directly observe today. This backward extrapolation is what we call the Big Bang, but here is where things become subtle. The Big Bang does not describe the creation of space from nothing. It describes the evolution of space from an extremely hot and dense state. It does not tell us why the universe exists, only how it has changed. When we say the universe is expanding, we do not mean that galaxies are flying into pre-existing emptiness. Space itself is expanding, and everything within it is being carried along. There is no center of expansion, and no edge that the universe is expanding into. Every point in space can be thought of as the center. This alone already challenges our everyday intuition, but the deeper issue lies even further back in time. As we approach the earliest moments described by the Big Bang model, our equations begin to break down. Temperatures rise beyond anything we can reproduce. Densities approach infinity. Time intervals shrink toward zero. Eventually, we reach what physicists call a singularity. A singularity is not a real physical object. It is a signal that our mathematical tools have failed. It tells us that the theory we are using no longer applies. At this point, the equations stop making sense, and the concept of time itself becomes unstable. This is where many misunderstandings arise. People often ask what happened before the Big Bang, but this question may be flawed from the very beginning. If time itself emerged with the Big Bang, then asking what came before it may be like asking what is north of the North Pole. The problem is not that we lack the answer. The problem may be that the question assumes a framework that no longer exists. According to general relativity, space and time are not separate entities. They form a single structure known as spacetime, and this structure can bend, stretch, and warp under the influence of energy and matter. When we trace spacetime backward to the earliest moments, it may simply stop in a way that has no meaningful before. Yet this does not mean that the Big Bang was the absolute beginning of everything. It only means that our current theories cannot see beyond it. To understand why, we need to recognize a crucial limitation. General relativity, the theory that predicts the Big Bang, does not include quantum mechanics, and quantum mechanics governs the behavior of reality at extremely small scales. Near the beginning of the universe, these two frameworks collide. Gravity becomes quantum, spacetime becomes unstable, and our best theories contradict each other. This is why many physicists believe that the Big Bang singularity is not real, but an artifact of incomplete models. Something else may have existed before the hot, dense phase we call the Big Bang, something that our equations are not yet capable of describing. One possibility is that the universe did not begin at all. Some theories suggest that the universe existed in a prior state, perhaps contracting before expanding again. In these models, the Big Bang is not a beginning, but a transition, a bounce from a previous cosmic phase. Other ideas propose that time itself may be cyclical, with universes endlessly forming, evolving, and dissolving, without a true starting point. There are also models in which our universe is just one region of a much larger structure, a multiverse where Big Bang-like events occur repeatedly, each giving rise to a new pocket of spacetime. In such scenarios, asking whether the Big Bang began everything becomes a much deeper question. Everything we can observe may have a beginning, while reality as a whole does not. What all of these ideas share is a common theme. The Big Bang marks the limit of what we can currently understand, not necessarily the origin of existence itself. It is a boundary, not a birth certificate, and this boundary forces us to confront a deeper issue, one that lies at the heart of cosmology and philosophy alike. What does it actually mean for something to begin? When we talk about beginnings, we usually imagine a cause, something that happened first, triggering everything that followed. A spark, an action, a moment where the story starts. But in cosmology, the idea of a beginning is far less clear. In everyday life, time flows smoothly, one moment leading to the next. Causes come before effects. Past, present, and future feel sharply defined. Yet near the Big Bang, this familiar structure begins to dissolve. If spacetime itself emerged from an earlier state, then causality as we understand it may not apply. There may be no meaningful distinction between cause and effect, no clear sequence of events, and no external clock ticking away in the background. This is why many physicists believe that asking for a cause of the Big Bang may be fundamentally different from asking for the cause of everyday events. To better understand this, scientists have explored ideas that extend beyond the standard Big Bang model. One of the most influential is cosmic inflation. Inflation proposes that the universe underwent a brief period of extremely rapid expansion shortly after the hot, dense phase began. During this phase, space expanded exponentially, smoothing out irregularities and explaining why the universe appears remarkably uniform on large scales. Inflation helps explain why distant regions of the universe look similar, even though they should not have had time to interact. It also explains why space appears geometrically flat, balanced precisely between collapse and endless expansion. Yet inflation introduces new questions. In some versions of the theory, inflation never completely ends. Instead, it continues indefinitely in the background, constantly generating new regions of spacetime. Our universe would then be just one bubble among countless others, each formed through its own Big Bang-like event. In this picture, the Big Bang did not begin everything. It began our observable universe. Time, existence, and physical laws may extend far beyond what we can ever observe. Other theories take a different approach. In bouncing cosmologies, the universe does not begin with a singularity, but transitions from a previous contracting phase into expansion. In these models, gravity becomes repulsive at extreme densities, preventing total collapse and allowing the universe to rebound. Here, the Big Bang is not a moment of creation, but a transformation, a turning point between two cosmic eras. There are also proposals suggesting that time itself may be emergent. Rather than being fundamental, time could arise from deeper quantum relationships that do not involve change or flow in the conventional sense. In such frameworks, the universe does not begin in time. Time begins within the universe. This idea challenges our most basic intuitions. If time is emergent, then the question of what happened before the Big Bang may be meaningless, not because nothing existed, but because before is not a fundamental feature of reality. Some physicists and philosophers take this even further, suggesting that the universe may be timeless at its deepest level, with all moments existing equally, while our experience of flow arises from consciousness and memory. In this view, the Big Bang is not the start of a process, but a boundary in how processes can be described. It is the earliest moment our models can reach, not the first moment that ever existed. This perspective reframes the entire question. Instead of asking whether the Big Bang began everything, we might ask something else entirely. Why does reality allow a universe like ours to exist at all? Why do physical laws permit structure, complexity, and time-bound observers capable of asking these questions? These are not questions with final answers. They sit at the intersection of physics, philosophy, and human curiosity. And this is where the Big Bang truly matters, not as a definitive explanation, but as a reminder of how limited our understanding still is. The Big Bang marks the edge of our knowledge, a place where equations fall silent and imagination must proceed with humility. It tells us that the universe has a history, but not necessarily a beginning. That time has a structure, but not necessarily an origin. And that existence may be deeper, stranger, and more subtle than any single theory can capture. Perhaps the most honest answer to whether the Big Bang began everything is this: we do not yet know. And that uncertainty is not a failure of science, but its greatest strength. Because every time we push against the limits of what we understand, we discover not just new facts about the universe, but new ways of thinking about reality itself. Beyond time exists for that reason, to explore questions that resist simple answers, to linger at the boundaries of knowledge, and to accept that some mysteries are not meant to be solved quickly, but contemplated slowly.